Okay, we're going to continue on with section 4.3, projectile motion. There's quite a few, um, there's about 27 slides in this section, so we're going to do it in parts. We're going to start off with this intro. That's the last slide from the previous lecture. So we're going on with projectile motion. And if you've ever observed a baseball being thrown in motion, you've observed projectile motion. Uh, it's simple to analyze if we make a few assumptions. First of all, we assume that the only acceleration is downward. A sub y equals g, and that's 9.8 meters per second squared directed downward. We also assume that there is no horizontal acceleration. In other words, a sub x is ax is equal to 0. And we also make the assumption that the effect of air resistance is negligible. And that's not always the case, but for studying it, for first learning about it, we can certainly make that assumption. And for some of the initial speeds that we'll be working with, that is a valid assumption that air resistance is negligible. If you start getting into large distances and high speeds, like someone, skydiver jumping out of a plane, he will reach terminal velocity. But we're not discussing that right now. Okay, with these assumptions, the path of the projectile is always a parabola. So we're going to use these assumptions throughout the chapter. If you look at the figure there, the only acceleration vector in there is g, and it's constantly downward, irrespective of the vertical component of velocity. You can see sometimes the vy is upward, sometimes the vy is downward. You'll notice the vx is always vxi. In other words, it doesn't change because there's no horizontal acceleration. All right, let's go to the next slide. For acceleration, the only acceleration is the acceleration downward due to gravity. We have the equation R final equals R initial plus V initial t plus 1/2 gt squared. The book has V final. I mean, the slide has V final. If you look in the book at it, at equation 4.1 on page 75, it is indeed V initial, not V final. That's a publisher error on these slides. I can't change it. I tried to change it. I can't change it. So I just wanted to point out to you that it's V initial t. The initial x and y components of the velocity are V initial times cosine theta initial, and the Vy initial is V initial times sine theta. So we're getting the components of the velocity vector, the horizontal component and the vertical component. So the figure is a pictorial representation of the projectile launch from the origin. That is, R initial equals 0. The final position is a superposition of the initial position, Ri, V initial times t. The displacement of no acceleration were present, and 1/2 gt squared that arises from the acceleration due to gravity. If no gravitational acceleration, the particle would continue to move along a straight path in the direction of V initial. The vertical distance, 1/2 gt squared, through which the particle falls off the straight line path, is equal to the same distance that the object dropped from rest would fall during that same time interval. Okay, let's okay, the projectile motion, the acceleration ax is equals 0 in the x direction, and the constant acceleration ay is equal to g in the y direction. When solving projectile motion problems, we use two analysis models: a particle under constant velocity In the horizontal direction, that's Vx final equals x initial plus Vxi times t. And the particle under constant acceleration in the vertical direction. And that's, well, there's a lot of particle under constant acceleration in the vertical direction with x changed to y and ay is equal to minus g. I prefer using g equal to minus 9.8 meters per second squared, but you can work it either way as long as you stay consistent. So the horizontal and vertical components of the projectile's motion is completely independent. They can be handled separately with time t is a common variable for both components. So you can see the equations here. Vy final equals Vy initial over gt. The Vy average is Vy initial plus Vy final over 2. These are basically just your kinematic equations of motion listed here because since it's constant acceleration, we use these kinematic equations. Let's do a quick quiz. As a projectile is thrown at an upward angle in its parabolic path, at what point along its path are the velocity and acceleration vectors for the projectile perpendicular to each other? Is it A, nowhere, B, the highest point, or C, the launch point? I'll let you think about it a little bit. And it is at the highest point. Why? Well, if you think about it, at that point, at the highest point, the vertical velocity is actually 0, and so the velocity is only the velocity in the horizontal direction, the Vx velocity in the x direction, and the acceleration is g, and it's downward. So you've got the horizontal velocity going this way, and the acceleration, the gravitational acceleration vector going down, and they're perpendicular to each other. All right. At what point are the velocity and the acceleration vectors for the projectile parallel to each other? Nowhere, the highest point, or the launch point? So is there any point where the velocity, and we're talking total velocity, not just velocity in the x direction or velocity in the y direction, we're talking the total velocity. Is there any point where it is the same as the acceleration downward? And the answer is no. It's nowhere. At nowhere are the projectile, at nowhere is it equal, are they both parallel? And with that, let's see, yes, we will continue. We're not through with section 4.3, projectile motion, but we will continue our discussion as we discuss height and range of a projectile in the next video.